I'm Rakshith. So I'm a student, master student in IIT Hyderabad itself. So yeah, good evening once again. So today I'm going to be speaking on the topic. Uh, we have come up with a framework, a robust framework to combine multiple point clouds from LiDARs. So this is actually designed for autonomous ground vehicles. We have uh, we have designed this keeping autonomous ground vehicles in mind. So suppose we have multiple LiDARs into coming into picture. We have developed a small framework to process the data and get a robust output. So as we know, LiDARs, cameras, and radars are the three main sensors for autonomous ground vehicles which we use right now. And just a thing, a small bit about LiDAR. LiDAR is a sensor which emits light rays, laser pulses, and when it hits a surface and reflects back to the sensor, so it calculates the time taken for this phenomenon and gives the coordinate of the point, 3D coordinate of the point. So this is a I've just given a raw data output of how a laser LiDAR sensor gives an output. These are the points in 3D space. So our main aim was to combine the point cloud from multiple LiDAR sensors and which are calibrated. So the main motivation for this was we have a autonomous campus shuttle running in our IIT Hyderabad campus. So usually what we do is we place a LiDAR sensor at the top of the vehicle. So it actually takes care of the localization, mapping, and obstacle detection tasks. So one issue which we face is whenever it is close to the vehicle, whenever it is close to another vehicle, or if someone from behind comes close to my vehicle, there is something called a blind spot in sensors. So since the LiDAR is placed on the top of the vehicle, there was a blind spot created, which was very significant. Our main aim was to reduce this blind spot. So we came up with combining point clouds with two multiple LiDAR sensors. So this is a small setup we came up with. We replaced the LiDAR at the top with two LiDARs, one at the front right corner and another at the back left corner. So coming to the methodology, okay. So this is the blind spot. This is just a small visualization of how the blind spot is. This is the LiDAR placed on top of the vehicle. It can see something in this conical region, and the purple region below this is something called the blind spot. The LiDAR won't be able to detect any obstacle which is present there. So in our new setup, we have reduced the height of the LiDAR mounting. So naturally, the blind spot is also decreased, and we have placed the LiDAR in such a way that the 360 area around the vehicle is covered. So we in the table you can see that the blind spot area is reduced significantly. Before it was around 142 meters square, and it is reduced to 15.8 meters square around the vehicle. So this is the flow of the methodology. First we take in the raw data from the LiDAR sensors. We do a process called temporal alignment, which is the LiDARs emit rays at particular time frame, and what temporal alignment does is it synchronizes the data from both the sensors with respect to time. And there's one process called spatial alignment, which so that the data in space it will be calibrated in this process. And at the end, we do the concatenation of both the point clouds together to get the final output. So the first process in this is the temporal alignment of the data. We use a ROST robot operating system package, which is already open source, present open source. We use something called the approximate time filter for this. So what it does is, if even if the LiDARs are emitting data at unequal frequency, it kind of matches the frames together and gives a synchronized output in the temporal alignment. So the next thing which we require to calibrate these two sensors together is the spatial pose of either sensor. Once the sensors are mounted on the vehicle, we need to exactly know where that sensor is in space with respect to a global frame. For this, what we do is we create something called a LiDAR HD map. We collect raw data from a sensor and use an algorithm to stitch the frames together. And we do something called localization. Localization is nothing but we already have a global map, and we localize the LiDAR. The LiDAR gets to know where I am at that particular with respect to a global reference or map. So we do this process called localization for both LiDARs. So I get, with respect to origin, I get the pose or position and the orientation of both the LiDARs. So this is the process of how we localize both the sensors. This is for the first front LiDAR, and that will be for the back LiDAR. We get parameters like X, Y, Z, which are the Cartesian coordinates of the LiDAR. And we get Gottonian coordinates, which tells us the orientation of the LiDAR with respect to a global frame. Once we get this position, pose 1 and pose 2 of both the LiDARs, we do something, we transform both the point clouds basically. So how we do that is we have both the pose X, Y, Z, and this is roll, pitch, and yaw. We take all these parameters and pass it through transformation, which is basically a 3D transformation of in geometry. So we this PI over here is a raw data point from each LiDAR, and P dash PI dash is the transform point. We just multiply with the calibration matrix M, and we get a transform point cloud for both the LiDARs. And once that transformation is done for both the LiDARs, we concatenate both the point clouds using the PCL library, which is again an open source ROS package, which is available. So it looks something like this. When we mounted LiDAR 1 and 2 on the vehicle, we set the field of view in such a way that the LiDAR data which falls on the vehicle is neglected. So once these two, once the data from these two LiDAR comes separately and goes through our algorithm, it is now able to synchronize with respect to time and space and give a combined point cloud like that, which you can see on the right. So once we have a concatenated point clouds, we can go ahead and use it for our localization as well as perception purposes. The advantage now will be the blind spot will be drastically reduced, which was previously the case. So maybe mapping localization or the obstacle perception, the task can be done using this concatenated point cloud. So this is a visualization of how the point clouds appears once the data is combined together. So yeah, to conclude, our algorithm, what it does is it is a simple extrinsic calibration, which is both spatial as well as temporal. And so the main problem it is solving is it is reducing the blind spots which naturally occur due to the sensor. So I want to acknowledge my professor Rajalakshmi, and this is a small picture of the lab which we work. That's a test bed where we conducted all the experiments regarding. Yeah, that's it. Thank you.